Welcome back to Principles of Engineering. Today we're talking about force vectors, and this is a quick review of what we learned before about vectors, and then some additional techniques for breaking them into their components, and then adding vectors to get a net resultant vector. So just a quick review on what a vector is. A vector quantity has both a magnitude and direction. Some examples are position, force, that's what we're going to deal with here, and moments. The vector notation is given by a variable such as a or b, and usually the handwritten notation is a with an arrow over the top of it or b with an arrow over the top of it. That font got a little bit messed up there. So let's look at how we can illustrate a vector. And in this instance, I've got a vector and it's got a magnitude. And the magnitude is 3 units, whatever the units are, newtons or whatever. 3 units. So that's my magnitude of my vector. Now the direction of this is the angle relative to some reference. In this instance, it happens to be the positive x-axis, so it's 30 degrees counterclockwise from the positive x-axis, so magnitude direction. A sense is which way is this thing going, as measured from its base to the arrow tip. And from the base, to get to the arrow tip, I have to move right and up. Now for trigonometry review, we're just looking at the ratio of the sides. And we look at a right triangle, that's what we're really doing here. And the ratio of the sides is based upon us standing at the base of the angle looking across. And when I look across that, the opposite side is what I'm looking at. My feet in this little diagram are what I'm standing on the adjacent side, and the hypotenuse joins those two and forms the angle. Now for right triangle trigonometry, what we're talking about is a triangle with a 90-degree angle, which this has, and we know that the interior angles always equal 180. We also know Pythagoras' theorem, and that just says that the hypotenuse squared is equal to the opposite side, the a side squared, plus the adjacent side, the b squared side. Now notice it doesn't require any kind of magnitude on that. It doesn't matter whether it's a positive a or a negative a. When I square it, it always becomes positive. So that's Pythagoras' theorem. We'll use that later on. Now the functions for the trigonometry review that we looked at last time was so, ca, toa. That's our mnemonic. And what that means is if I stand at the angle and it rises up out of the ground and I'm looking at the opposite side, the relationship between the opposite and the hypotenuse, that ratio is the sine of the angle. Similarly, the ratio between where my feet are, the adjacent length, and the hypotenuse is the cosine of the angle. And the last relationship we're going to talk about is the ratio between the opposite, where I'm looking, and the adjacent, where my feet are. That ratio is defined as the tangent of the angle. So let's look at a little bit more in this mnemonic. When we say so, that just means that the sine is equal to the opposite over the hypotenuse. Ca means that the cosine is equal to the adjacent divided by the hypotenuse. Toa means the tangent is equal to the opposite over the adjacent. Easy to remember that way. So let's look at our trigonometry application here. If I have a hypotenuse of length f, I can break that into 2 component vectors. The adjacent side vector, f sub x, and the opposite side vector, f sub y. Now notice x and y are just that, x movement and y movement. They may or may not be the adjacent or opposite, depending on where you're measuring your angle from. So the hypotenuse is the magnitude of the force F. So in this figure, the adjacent side is that x component, f sub x. The opposite side is the y component, f sub y. That's trimmed off a little there. It's trimmed off. It should be f sub y. It looks like f sub v. So as I look at this thing, I can say that the sine of the angle is f sub y, that is the opposite side, divided by f, which is the hypotenuse. And I can say the cosine is f sub x, the adjacent side length, divided by the hypotenuse. And the tangent is f sub y divided by f sub x. Easy. What's really useful now is I can define the opposite side by the relationship that f sub y is equal to the hypotenuse times the sine of the angle. F sub x is the hypotenuse times the cosine, and we'll use that over and over. So here we have a vector A, and its magnitude is 75 pounds. The direction is 35 degrees counterclockwise. The sense is right and up. Now that sense is important because it's going to tell me that I have got a component that goes in x to the right and in y up. That's what that sense tells me. So I can use my relationships and solve for f a sub x, the component vector of a in the x direction. Now as you remember that, the relationship there is the cosine of theta is equal to the adjacent divided by the hypotenuse. I can solve that for f(a)x, and I get the hypotenuse, 75 pounds, times the cosine of 35. And that should be right. 61.4 pounds to the right. Now if I solve for f(a) sub y, I do that same relationship. The sine of 35 degrees is equal to f(a) sub y divided by 75 pounds. Or f(a) sub y is 75 pounds times the sine of 35. This time it is actually up. There it is in my calculator, and I get 43 pounds up. Now I can do that same vector going down at 35 degrees, and guess what? The numbers are the same. When I solve it, I get 61.4 pounds to the right, and I get 43 pounds down. Now it's important that we note that that 43 pounds down is negative. It's down, negative, because up, right, and counterclockwise are positive when we're dealing in statics. So now we can look at the resultant force. So let's look at this problem. We just did all the math to solve this. And in this problem, we're saying two people are pulling a boat to shore. They're pulling with an equal magnitude of 75 pounds. Vector A, vector B. Both vectors are 35 degrees off of the horizon. One below it, one above it. What I can now do is take those vectors and replace them by the components that I just calculated. Now, because I've put them in relation to the x and the y direction, I can now just mathematically add them by their signs. So I look at the forces according to the sense. So the force A has a sense right and up. B has a sense right and down. Those are the components. Now I can sum these forces, and I can say the sum F sub x and F sub y. So let's do that. When I sum those, and that's the sign sigma right here, sigma, sum the forces, I get the net force in x is equal FA sub x plus FB sub x. So 61.436 plus 61.436 rounds to 122.9 pounds. It's to the right, or it's positive. When I sum the forces in y, I get 43.018 pounds up and 43.018 pounds down for a net force of 0. So now what I can do is draw a resultant vector of both efforts. So my magnitude of my resultant vector is 122.9 pounds, and it's 0 degrees from the positive x-axis. The sense is to the right. So the net resulting vector, about 123 pounds, 122.9. That's the net vector. So that makes sense, and that's pretty easy because they're equal vectors, and I had one direction completely cancel out. The y is canceled out, so that was easy. Let's look at one that's a little more complicated. So here I have an I hook, and it's got 300 pounds pulling up and right, vector C, 400 pounds pulling down and right, vector D. Notice the angles are not equal. 60 degrees up for C, 30 degrees down for D. So first, I'm going to find the component vectors for vector C. So if I look at this, I can see that C is replaced by that right triangle. 300 pounds, 60 degrees is my angle. My opposite side is the y component. My adjacent side is the x component, or fc sub x. I can use my SOH-CAH-TOA relationship here. So fc sub x is equal to the force of vector C times the cosine, because it's the adjacent, and that's 150 pounds. It's positive because it's to the right. Fc sub y, similarly, is the force vector C, 300 pounds, times the sine of 60 degrees, and that's going up, or 260 pounds, positive again. So now let's look at the vector D. D goes down and to the right with 400 pounds. Again, I can replace it with its component vectors. Fd sub x is my adjacent side. The x component's my adjacent. Fd sub y is my opposite side. So now I can use my cosine relationship to find the adjacent, or 400 pounds, times the cosine of 30 degrees, and that's a positive number because it's right. It equals approximately 350 pounds. Fd sub y is the y component of that same vector, and it is 400 pounds times the sine of 30 degrees down. Now I can take and replace those two vectors with my components that I just found. So Fc sub y, 259.8 pounds, Fc sub x, 150 pounds, Fd sub x, 346 pounds, Fd sub y minus 200 pounds. Those are the components. And I can now add these components to find my resultant. So my resultant force is the sum of the forces. So I sum it in the x direction and then in the y direction. So the sum of the forces in the x direction is the force component of C in the x plus the force component of D in the x. I get about 496 pounds to the right. The sum in the y component is FC sub y, which was positive, it was up 259.8, plus FD sub y, which is negative because it's going down. That ends up adding to 59.8 pounds up. When I add these, I get my resultant vector. The sense is right and up. When I go to draw this, all I have to do is draw my x and y components. Now, there's two ways to do this. I can start at the origin with my x component, 496 pounds to the right, and then add the y component, 59.8 pounds up. And the resultant is that hypotenuse between those two sides. Or I could start out at the origin and move up. And then I could move over to the right. And there I have the exact same net vector. So that is my resultant force. So see, when I'm adding these x and y components, I just put the head of, or the tail of one vector on the head of the other. And that is how we add vectors graphically. So I have 59.8, 496.4, 59.8, 496.4. And using Pythagorean theorem, I can find F sub r, the resultant force. Here's the math behind it. A squared plus B squared equals C squared. And I find that my resulting force is 500 pounds. That's the magnitude. Now, to solve for direction, I need to use that tangent relationship. But I can't just use the tangent relationship because that won't give it to me. I need the inverse tangent relationship. And I'll pull up an on-screen calculator here in a minute and show you how to walk through that if you haven't done that. So if I know that the tangent is the opposite over the adjacent, then the tangent of the angle is 59.8 divided by 496.4. I can take the inverse, that's what this minus 1 means, inverse tangent of 59.8 divided by 496.4 and end up with my angle for the tangent. So let's pause and open up a calculator and I'll show you. Okay, here I've got my Windows calculator and I'll just plug my numbers in. So it's important if you're going to use this calculator that you understand the way to get to the trigonometric functions is first of all be in the scientific calculator. So that's the type that I have right here, scientific. Next is be sure that you're in degrees. Degrees, radians, grads. Degrees is what we want to be in. And now under trigonometry, the second function is where I'm going to find the inverse tangent. So let's do this. 59.8 divided by 496.4 equals 0.12, and now I go trigonometry, second inverse tangent, and I get 6.869, or about 6.9 degrees. And we round that to 7 degrees. So there's my resultant force. The direction is 7 degrees counterclockwise from the positive x-axis. Sense is up and right. And that's all there is to solving these problems for net resultant vectors. So we're going to do some work on this. The next exercise, is 2.1.4b, which is force vectors part 2. We'll work together in class and get a little bit more familiar with this idea. But remember, if we take a vector and we break it down using our trigonometric functions into its x and y components, we can then add multiple vectors together to get the net resultant vector. That is the essence of doing our statics, the trigonometry that we'll do in statics. This is a practice of adding those force vectors. Thanks for watching.